sound. Okay, we're recording.
Yeah, okay. Yeah, hello folks. Well, um so I haven't I'm kind of confused about consciousness, but I thought I'd make a little model of cognition. And this is joint work with my long-term colleague Hadi Majid. Hmm. Oh, there we go. So this model comes out of a couple of findings that are kind of out of the way, maybe even preposterous. And these are let me just do something so I get these things out of the way. Yeah. Yeah. Um, it comes out that all logical explanations of evidence are expressible, logical, I emphasize, by the same networks of elementary operations found in digital computers. So we're going to have a very simple form to express what computers can do. And now I'm having a weird time. Okay. And then, and the second preposterous finding is this proof I've talked to folks about before in quantum theory that makes a place in science for imagination beyond logic. So I propose to model cognitive processes in people and other organisms as digital networks, but networks that get rewired while they operate. And these findings are preposterous only because of old-fashioned ways of thinking, which just gets to that nice book, The Blind Spot, which I'll talk about at the end. So we're organized as follows. There'll be some introductory remarks. The technical guts of this proposal is token games on marked graphs. We'll talk about that. And after we get the model described in that way, I'll talk more about those findings in items 3 and 4 and turn to the blind spot in item 5. So the introduction, what do I mean by cognition? I mean something that's essential to every organism from bacteria on up to people. And it's the linking of memory to stand between sensing and acting on an organism's environment. And by the way, I welcome questions and interruptions if somebody needs, if there's a need to clarify something. So, cognition depends on biochemical and nervous networks. And I model cognitive networks by digital networks that undergo unpredictable changes prompted by surprises. And in this talk, I want to be quite explicit about how to represent a digital network. Cognitive networks share two properties with digital networks. One, they involve computation and commutation and communication. And secondly, unpredictable changes happen, often prompted by surprises. So when I'm talking about a digital network, I include the guy up on the telephone hooking up new customers or fixing storm damage. And when I talk about cognitive networks in people, people are rapidly changing creatures that don't get born with an adult nervous system. I'll talk some about surprise. By surprise, I mean something beyond what can be given a probability. And unknown, unknown. The surprises that I typically value in a day is I'm working on some project and then I don't know what to do. I get stuck. So I kind of chill out for 20 minutes or maybe doze, and then I know what to do next. That comes as a surprise. The idea of networks is quite visible in neurophysiology. This is a little graph diagram from Buzaki's book, The Rhythms of the Brain. And it's a graph in the sense of nodes connected by arrows. I'll use a lot of those, but they'll come with tokens. So we're into the second part here, modeling a cognition by token games on marked graphs. The graphs are arrows and nodes as we just showed. Here's a digital network for a thermostat shown as a marked graph. The marked graphs are graphs with nodes and arrows. You put tokens on them. Here's one for the old setting. Here's one for temperature from an environment. A node fires, it slurps up, takes up these, and puts a token on its output. There's only one output here. And this defines a kind of game on a graph played with these tokens that carry messages. So here's the little bit more detail. The game is played by a firing rule, which is what I just said. When tokens are on all the arrows into the node, they come off the input arrows and get put on the output arrows. And the tokens carry labels. Uh, at the finest level of description, a label's just a 0 or a 1. For digital networks linked through feedback to an environment, one or more nodes is labeled for the environment, and that may have no definite rule for labeling. It's open. That's an example not of the unknown unknowns, but of just handling known unknowns. The zeros and ones that I talk about can be implemented by any two physically distinct conditions.
Question. I'm sorry. I'm just. I want to go back to the definition of the token game. Okay,
Yeah,
so is it possible to have a fire? You have to have so as I understand it, you have to have tokens on all arrows in order for the thing to fire, and then all the tokens get removed and get put on arrows pointing out of the node. So there's no such thing as an arrow going in where it can fire if it doesn't have a token, and there's no such thing as automatic tokens being on input nodes. It has to come from the input to the output. Is that right?
that's right.
Okay.
Yep. Thanks for asking. So, 0 and 1 aren't anything mysterious. If you have a light switch, 1 can be up and 0 can be down. They're physical. Now, those are networks. So far it just looks like computers. Now I want to get to the part where a cognitive network undergoes changes. This is a series of 5 drawings of an amoeba inserting itself into a filament of a slime mold of which it will be a part. These are cellular slime molds. And the amoeba involved, sometimes the amoeba are free swimming creatures, but they form fruiting bodies and make these filaments. So you see an amoeba that's bumped coming from the left, that's just bumped in here, and it manages to insert itself into the fiber. And the thing I wanted to represent with the marked graph was how that could happen while preserving a change of biochemical communication up and down the whole fiber. So in the marked graph picture, here we are. And so you've seen the tokens. I've left off the labels because they don't matter for this part. And you see a net approaching, a graph approaching another graph. The other graph, first step is to insert a new node into it, which is this little red square. Those two nodes from the separate pieces can join, and all this can happen while preserving the firing rules. Then the problem is, the problem was how to insert that without interrupting the chain of communication. And it's done here by joining in two places. It will join here, there, and then after the joining, this original connection can break, but still leaving a chain all the way through. And that's my model. That's how I want to think about cognition, where there's computing stuff going on, but there's changes in the wiring while it happens. Now I want to talk about the computing part. We're used to thinking about computing from a von Neumann model or a Turing model, and I want to do something else about it. I want to say that first I'm hardware oriented. So what is a modern digital computer built out of? Well, it's built out of pieces that get stuck together, and the pieces are finally built out of just two very simple things. There's a NAND gate that's, I'll show you in more detail, and there's a fork that's just the branching of a wire. And here they are. I don't know if everybody's familiar with NAND gates. Does anybody want to give me a clue about that? Hold up your hand if you're familiar with an AND gate. Yeah, okay. Some, but not all. Well, okay. The NAND with the N is named for a negation of an AND. The AND logical operation is the thing that if it gets two inputs that are ones, it puts out a one, and otherwise it puts out a zero. The NAND operation does it just the other way around. And the fork operation is illustrated on the right here, which is just essentially a branching in the wire. Whatever comes in gets doubled and goes out. I got familiar with these when I was actually building digital circuits, and I had occasion to use the Texas Instrument Integrated Circuits catalog, which quite delighted me because all the various things like shift registers and adders were indeed built out of NAND gates and forks. Here's an example of a 1-bit adder built out of NAND gates and forks. And that pervades everything in your computer. What the silicon chips do is provide an abundance of NAND gates and forks arranged in various patterns to make memory, arithmetic units. Everything that's in there is made out of NAND gates and forks. Often, when you're describing a computer, you use a coarser description, so the add may turn out to be a little box and you don't draw all the parts. There's a serious need to use coarser descriptions because at the level of NAND gates, the laptop can have over 1 billion of them, and the big computers can have many times more than that. A few points I want to make here. I want to clarify that this representation does not include a Turing machine. It includes whatever can be done by finite means. That's a big contrast with the Turing machine. And, and our computers, if you're using a mathematics program like MATLAB, and you keep exponentiating the number pretty quickly, what prints out is NaN, which stands for not a number, which means you've gotten bigger than the machine can hold, which happens whenever there's finite resources. So this network of nans and forks, we're not playing Turing, we're representing whatever can be done with by finite means, whether it's human hardware or a logic pattern we see in a bacterium. Second point is that logical operations are essential to life. And my prime example is the copying of DNA with very few errors and its regular translation into other molecules. And so whatever arithmetic and logic operations you attribute to that can again be built up out of nouns and forks. I was kind of a little surprised the other day to find a quite different argument coming from a psychiatric point of view. That's cited in the references at the end of this talk. So I'm stressing again that life involves more than computation, the unpredictable changes. And what do those changes mean? It means the networks undergo changes in their wiring, the way the nouns and forks are connected. They can acquire new nodes and connections, they can lose them, they can merge, they can split. And one of the papers cited at the end, you can read more examples. And I think of unpredictable rewiring of logic happening also, for example, in me. When I don't know what to do and I'm at a loss, and then suddenly I know what to do, well, I model that as a rewiring. The second finding on which this was built was this famous proof I keep talking about. There's a proof in physics that conflicts with the hope that physics can converge on final truth. And the proposition is that given any set of probabilities of outcomes of an experiment, an infinite set of quantum explanations fit. And although they fit, they conflict in their predictions of further evidence. Johann has stressed before that quantum mechanics has a place for unpredictability. Given the state, you may not know the outcome. This is a distinct business in that you can't find out the state without some guess. This is kind of obscure to a lot of people because the courses in quantum mechanics, the theory courses, emphasize suppose you have a quantum state, how do you calculate probabilities from it? But question, where does the quantum state come from? My favorite example is probably the Stern-Gerlach experiment, where they were making measurements to decide between a classical model and a quantum model. The classical model said there ought to be one bump in the data, and the quantum model said there ought to be three bumps in the data. And what they found was a distribution with two bumps. So there they had the data, but it didn't come from their hypothesized quantum state, so they had to figure out a different quantum state. And that was the way that spin got invented. But the point is that to say you're given the quantum state poses the question where that comes from. And my argument is it comes from experiments. And then quantum mechanics has this interesting language that it has one kind of math for outcomes of experiments, which it idealizes as probabilities. Of course, a real experiment, you only get relative frequencies on a finite set. But suppose you could get the probabilities, it still doesn't determine a quantum state. And the implications of that choosing any explanation takes a guess, an unpredictable act of imagination, I would say. That's one implication. And that makes new data can invalidate the guess. So the future's always open to surprises that call for revisions. And the last point is that means there are no final answers if you want to be consistent with quantum theory. Now, why do these things seem kind of out of the ordinary? Well, so there's a recent book by Frank and Gleiser and Thompson, this book I've pointed to and thought people can read the first part of the book off Amazon without even buying it. But it's saying these findings seem preposterous because of traditions of investigation. And people tell me the scientific inquiry goes back to the Greeks. And I was recently having another look at Plato's Timaeus, which I've had since I was a kid in college. And sure enough, he's making a distinction between celestial and earthly. And celestial is mathematical and perfect, and earthly is a wobbly approximation. So the whole emphasis translated a couple millennia forward is the equations are what matter, and if the experiment doesn't quite match them, that's the experiment's problem. And so I remember my first effort to recover was figuring out, holy cow, I do not live in space-time. Space-time shows up when I'm standing at the blackboard and there's a left parenthesis, capital M, comma G, close paren, and I point to that and say, well, that's naming a space-time with some metric G. I don't live in it. I talk about it. And so one of the big points in the blind spot is that if you're in physics, it's easy to forget that the formulas are distinct for what they're used to describe. That, when you forget that, it makes some weird puzzles. For example, in classical electricity, you have a point charge electron, and you know how to calculate the field, which is a 1 over r squared radially outward, and you know how to calculate the energy of the field, which is just take the square of the absolute value of the field and integrate. And when you do that, you get an infinite answer. And so if a physics student, you ask the professor, what's up with that? He says, well, don't do that. And and the formula is telling you a lot of useful things about electricity, but it's a view from an angle, and all the equations are views from some angle. Another point that that nice book makes is, to borrow a phrase that Robert Crease calls the scientific workshop, and it's pointing out that when we learn something about electricity or magnetism or a piece of nature, we've taken something and isolated it. That's been mentioned in some talks before. They aren't here today, but Martin Korth noticed that science loves strict repeatability. Yeah, Kathy? Can you unmute yourself, Kathy?
Yeah, hi. Okay, what was the question again?
Well, you had your hand up, that's all.
Oh, no, I didn't intend to put my hand up. I'm sorry.
Okay,
I thought you were asking me a question. I apologize. I that was a mistaken mouse click.
okay, yeah. So, Martin stresses science like strict repeatability. Well, of course, that doesn't give a great platform for dealing with things that are intrinsically unpredictable. And
Well, now I would put my hand up and say that there's an awful lot of probability in science. So, I mean, quantum events are unpredictable, and so is thermodynamics, and so is economics, of course, and social science. And there's a lot of but the probabilities are predictable. And the idea is to find stable laws, but the outcomes are often uncertain.
yeah, well, back early on, I mean, I'm glad you pointed to that. Back early on, I was talking about surprise, and I wanted to distinguish a surprise using the nice distinction between known unknowns and unknown unknowns. That the kind of unpredictability I mean here are the unknown unknowns, to which you don't assign any probabilities because you never thought of them before. Does that make any sense